happy Wednesday morning. We finished up the introduction to functions. Spend the rest of the semester studying different types of functions. Starting with one that you're already familiar with, polynomial. So in algebra, we kind of studied what a polynomial was, and that was kind of it. You did solve quadratics, solved easy cubics, and cubics that are easy to factor. That's really as far as you went. We're going to go further. Study polynomials more in depth and with finding the zeros of any degree polynomial. We begin with the most basic polynomial, known as a power function. Power function is just a function of the form k x to the p, where k and p are real numbers. K is known as the coefficient. What you see right now is x squared. There's x to the fourth. X to the sixth, eighth, so on and so forth. So if I just let this play out, it goes up to the 20th. You can see how the general shape itself stays the same. This will be important. So these are for all the even powers. Second power, fourth power. So that right there is x cubed. X to the fifth, x to the seventh, the ninth, so on and so forth. And again, notice that the general shape stays the same. This will again become very important. This is just kind of summarizing it. The end behavior, if it's an even power, it it increases without bound on both ends. Odd power, decrease without bound on the left, increases without bound on the right. Now this is if your coefficient is positive. So what do we think happens if the coefficient is negative? So what does it do on the even? What about the odd? It's just the opposite. Right, so for a negative coefficient, your even power function will decrease without bound on both ends. The odd will increase without bound on the left, decrease without bound on the right. These two slides, keep them in mind. Now we move on to the polynomial function. What did they tell you polynomial was in algebra? It's actually just a sum of terms where each term is a product of integer powers, positive integer powers. Restrict that a little bit. Polynomials with polynomial function. Polynomial function, any function of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus so on and so forth, plus a sub 2x squared plus a sub 1x plus a naught. This is what's known as the general form of a polynomial. Notice that the general form has the powers in descending order. Each of the a sub I is called a coefficient, and they can be any real number, with one exception: a sub n cannot be 0. Now, technically, the a sub i's can be any number, not just real numbers. They could also be complex numbers. And then you have a complex valued function. For our purposes, we're going to stick with real valued functions. So all the coefficients will be real numbers. Each product, a sub I x to the I, is a term of the polynomial. And n is a non-negative integer. That is called the degree of the polynomial. So your degree is just the highest power that appears. The term a sub n x to the n is called a leading term, or is the leading term. A sub n is the leading coefficient. A naught is the constant term, or just simply called the constant. Being able to identify the leading term and the constant is very important. So the end behavior. Let's quickly go back. Look at that function. End behavior. The right-handed end behavior would be very large values of x, right? Think of an extremely large value of x. $37 trillion. Let's do this. Let's just do this. $37 trillion cubed versus 37 trillion squared. $37 trillion cubed is really not noticing it. 37 trillion to the first power, again, it's not really noticing. And adding one, it's definitely not noticing it. So really, for very large values of x, that x cubed dominates. Right? None of the other terms really matter. They're negligible. So this polynomial on the ends will behave like x cubed. left-handed behavior would be very large values in the negative direction, right? So like negative 37 trillion. Cube that. Negative 37 trillion squared. Is it even going to notice? Negative 37 trillion, again, it's not really going to notice. And then plus 1, really not going to notice. So once again, that x cubed is dominating the entire function. So on the left-handed side, the function also behaves as x cubed. That is how we determine the end behavior of a polynomial. End behavior is just the end behavior of the leading term, the leading term, a sub n x to the n. Keep in mind that is only the end behavior. That tells us nothing about what's going on in the middle. Right? Because now for smaller values of x, all the other terms are no longer negligible. So they will affect the shape. It is generally very difficult to determine what the function does in the middle. And behavior is, generally speaking, very easy to figure out. What's going on in the middle that's difficult? We will do the best we can. Unfortunately, we're not going to be able to really analyze it until calculus. There's not a lot we can do until calculus.
Can you go back for 1 second? 4 seconds. Please, thank you. Yes, you good. Thank you.
The idea of a turning point. All right, well, before I even put the definition, take an educated guess. What's a turning point?
When it reaches the point.
What terms? Yeah. Unmathematically, yes. Mathematically, it's where it's going to switch from increasing to decreasing or decreasing to increasing. So the y-intercept, remember what that is? It's the point at which the function has an input value of 0. The x-intercept, point where the output value would be 0. How many y-intercepts can a function have? So how many times can a function cross the y-axis?
More.
Be careful when you say 1.
2.
A maximum of 1 time. right? The function doesn't actually have to cross the y-axis. How many times can a function cross the x-axis? Theoretically, an infinite number of times. Here's one of my favorite functions. This is a case where it's crossing the x-axis an infinite number of times. Keep in mind, I'm really zoomed in on the center there. This only goes from -1 to +1 on the x-axis. If I zoom it out, oof, that's horrible. I don't even think that's 0, 0 anymore. It's not. Which is why we only care about there. Instead, let's zoom in further, though. I don't know. -0.5 to 0.5. Sorry. See what happens as we zoom in? Oh, not much. Notice what's happening as I get close, as I zoom in more and more. That shape really isn't changing, is it? So notice no matter how close we get, no matter how much we zoom in, it's still crossing the x-axis an infinite number of times. It's still very quickly oscillating. Do you think it has a y-intercept though?
Yeah.
What would the y-intercept be?
0. 1, 0, 0.
It actually doesn't. It doesn't actually ever cross the y-axis. This function's undefined at x equals 0, which is the only way you get. Actually, also that's how you get y equals 0. So you can't even get y equals 0. y-intercept is when x is 0. Forgot my coffee this morning again. X can't be 0. Ignore the SIN part of that in the semester. Because of that 1 over x. I get it. Really ridiculous. There we go. Eventually gets to the point where I forget when it was. Oh no, okay, I have that. There is a point which just looks like a solid mass. That's an example of a function that would cross the x-axis an infinite number of times. It's also a cool function. You should examine it again in Cap 1. Specifically, we'll be examining in Cap 1 what that function is doing as we approach the origin. And then just a graphical image of where the x-intercepts are, y-intercepts, and what turning points are. And so there's all of that middle stuff there. That's what's known as the local behavior. An important result of polynomials is a degree n polynomial will have at most n x-intercepts and n minus 1 turning points. So we can come back to this one and kind of guess, what is the minimum degree that this polynomial would have to be? Minimum degree. Three. It crosses the x-axis 3 times, so it has 3 x-intercepts. So that there tells you have to be at least degree 3. And then it has two turning points, so 3 minus 1 is 2. So the turning points tells you minimum degree 3. So minimum degree 3 here. I can't say definitively it is degree 3. Could be degree 5. Could be degree 7. I know it's not even degree because of the shape. But it could be any odd degree 3 or larger. I just don't know with this information. Yeah. Right, because if it was even, it would be either going up on both sides or down on both sides. I also happen to know that whatever the leading term is, the leading coefficient is going to be positive based on the end behavior. If a polynomial contains a factor of the form x minus h to the p, then the behavior near the x-intercept, it should actually be at the x-intercept, but near the x-intercept is determined by the power p. So we all remember what a factor of a polynomial is. Right? You spend a lot of time in algebra doing that, factoring polynomials. In this case, we say that x equals h is a zero of multiplicity p. So the zeros are where it's going to cross the x-axis. Or I don't want to say cross. It's where you have an x-intercept. What it does at that intercept is determined by the zero's multiplicity. If the multiplicity is even, it will touch the axis. If it is odd, it will cross the axis. So how can a function touch the x-axis but not cross it? If it's open, then it's not even touching it. Open would mean it's not defined. And so think about it in terms of signs. The x-axis refers to what value for the output y? So if you're on the x-axis, what's y? 0. So above the x-axis would be what? Values of y would be what?
0 to infinity.
Positive.
Positive.
Below the x-axis would be, so if you cross the x-axis, then the y values are doing what?
Negative.
True, they can be negative. But what are they doing at the intercept if it crosses? What happens? Just do an easy one. Gotta be crossing the x-axis, right? What do we know about the values of y to the left? So they're negative. What about to the right? So what happens at the x-intercept? At the x-intercept does, but what's happening to the values? In this case, this is strictly increasing. To the left, they were negative. To the right, they're positive. So if it's crossing the x-axis, your sign's changing, isn't it? Yeah. Your values go from negative to positive, or vice versa, right? They could go positive to negative. So that's what happens if it crosses. So how can you touch the axis but not cross it?
Have like an example, like x squared. Like x can equal 0, but it can't ever have a negative output.
So all the values of y are what?
Greater than or equal to 0.
Yeah, I'll just do a simple one. So your signs would stay the same, right? It would stay positive or negative. What's the function actually doing then at the point? So that x-intercept is also a what? You said it earlier. It's a turning point. So zeros with even multiplicities are turning points. Zero is x-intercepts. It's where the function equals 0. Okay, that's nice. It actually remembered the animation. Can you think of a possible restriction on the multiplicities? Using that first statement. So have at most n x-intercepts, which means it has at most n zeros. So what's the restriction on the multiplicities? Well, that's definitely true. The sum of your multiplicities cannot be larger than n. If it was, then you'd have more x-intercepts. It can be less than n, though. So whenever we get a result in mathematics that has an actual name, that generally means it's extremely important. The intermediate value theorem, kind of. This is not the actual intermediate value theorem. It's a specialized case of it. It states if f is a polynomial and f of a and f of b have opposite signs, then there has to exist a value c between a and b where f is 0. And so notice f of a here is positive, f of b is negative. What the intermediate value theorem says, there has to be some point between a and b. So there has to be some point along here where the function crosses it. Otherwise, you can't get from positive to negative. Notice what it's not saying though. It doesn't say how many times the function is 0 between a and b. All it's doing is it's guaranteeing that there is a place where it's going to cross. Right, so it could do this. Could just draw a straight line between them. Might do this. Could do that. Could also do that. Cross multiple times. No, but the point is it's going to cross the axis. So it's going to have an x-intercept. That's what the intermediate value theorem says. Now again, I say this is kind of because this is working for polynomials. The intermediate value theorem is for any function that's continuous. We're given a polynomial. We're asked to identify the degree, the leading coefficient, and the constant. First, the degree. What is the degree? What's the leading coefficient? Why is it -2?
Because it has the highest exponent.
Well, coefficient of the highest power.
Yeah.
What's the constant? So would this polynomial be in general form? No, it's not. Write it in general form. What's the general form?
-2x² plus 7x plus 15.
What's the degree?
3.
What's the leading coefficient?
14.
And what's the constant?
8.
Is that in general form?
Yeah.
We like it in general form.
Okay.
General form is the most common form. There's actually a second common form that's used. It doesn't have a name. But instead of writing the powers in descending order, it's writing the powers in ascending order. So you write the constant first, and your leading term last. So you may see that as well. Specifically, a lot of computer algebra systems will write it that way. So just keep that in mind. What's the degree? So I have 0, I have 16. Now I have undefined, but you already gave me 0, so it doesn't count. It's neither of them. You were closer though, 16. Look at the independent variable for the function. What is it? So it's the independent variable for f. I just said it. Bless you. What is it a function of? Function of a. A is your independent variable. That means b is a constant. Maybe unknown, but it's still constant. So that's why it's 16b to the 4th. What's the degree? Y2. P is your independent variable. So you're looking for the highest power of P. What's the leading coefficient? Sure about that? This incomplete. So how did you get 30 as the leading coefficient? Is 30 the coefficient? $30M. What's attached to P squared? 30 and M. So that's your leading coefficient. What's your constant? M cubed is your constant.
So that's in general form.
This is not general form.
So what is the general form? 30. Oh,
That'd be your general form.
because M's not.
Yeah, m's a constant.
That why it's last.
Hmm?
Why is it last? Like 40M. It's cute.
Because m is just some constant.
Oh, okay.
We're not looking for.
Yeah. When you're, in this case, we're concerned with p.
Mhm.
It's a polynomial in p. We're not worried about multivariate yet. That's calc 3. First, I have to get the foundations of single variate. What's the degree? What's the leading coefficient? Good, 1. And what's the constant? So this question 6.5, I can't believe I didn't put a question like this up there. Same thing, we're identifying degree, leading coefficient, and constant. So let me actually do this. What would the degree be? What's the leading coefficient? What's the constant? Yes, sir. How'd you get the leading coefficient to be 1 here? You gave it to me, so how'd you get it? in front of the x squared. So when the leading coefficient does not exist then. Why is it 1? It's implied to be 1. Right? We never write that, right? We write that because it's implied to be 1. So just because you don't see a constant doesn't mean there isn't one. What is it? What's implied? Constant would be 0. Right? We're not actually writing plus 0 there, but it is implied to be there. Which is why in the definition of a polynomial, it was restricted that your a sub n could not be 0. Otherwise, I could theoretically write this as like 0x to the 10th plus 0x to the 9th plus 0x to the 8th, so on and so forth. And go, oh, look, I have a 10th degree polynomial. But why stop there? I could make this a 1,000,000th degree polynomial by making all of the coefficients 0. So we want to describe the end behavior and determine the maximum number of turning points. So in order to determine end behavior, I have to reset my pen. We need to identify the leading term. So what's the leading term? Leading term is 2x cubed. Remember, the end behavior of polynomial is determined by the leading term. We now have a power function, 2x cubed. What is the coefficient of the power function? Remember, power function is a function of the form kx to the n. What is k? 2. Is that positive or negative? So we have k greater than 0. What's n? Is that even or odd? So what's the end behavior? What does it do on the left? Think back to those 2 slides I told you were going to be important. So f of x tends to negative infinity as x decrease without bound, or f of x decrease without bound on the left. What does it do on the right? Yeah, f increase without bound on the right. So that's the end behavior for 2x cubed minus 9. What's the maximum number of turning points it can have? How'd you get 2?
N minus 1.
Degree minus 1. So it's gonna have either 0, 1, or 2, right? It can't have a negative number of turning points. That wouldn't make sense. What is the leading term? I agree there's a 1/3 in there.
Well, 1/3 x.
Not just 1/3 x. 1/3 x to the 4th. That polynomial is not in general form. Not even close. You'd have to expand out the x plus 1 to the 4th power first, then distribute the 1/3 through. But since we're just looking for the leading term, what is the leading term of x plus 1 expanded to the 4th power? Just x to the 4th. That's why it's a 3rd x to the 4th, and we don't care about the rest of it. If you're curious, that would be x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. I did go to Pascal's triangle with you, right? Yeah, I definitely had those. And the binomial numbers. So we're looking at difference quotients. So second day, I have to look at that. What's your constant? Again, I'm referring to power function. Constant of the power function, which would be the coefficient. What's your k? Is that greater than or less than 0? What is your power? Is it even or odd? So what is the end behavior? What does f of x do on the left? Positive constant, even power. Increases without bound. What about on the right? What is the maximum number of turning points? So you can have 0, 1, 2, or 3 turning points. In fact, here you're only going to have 1. We'll be at -1. Rain is expected to start. Of course, they couldn't have started during class and the day before class. It has to start after class.
What time after?
What is the leading term? Sure?
Yeah.
Good. -1/2 x cubed. What is the coefficient? What is k? Is that greater than or less than 0? What is the power? Even or odd? Negative coefficient, odd power. So what does f do on the left?
Does it increase?
You sure? Increasing without bound? Nope. It's increasing.
The left side's increasing, the right side.
Because it's a negative coefficient. Oh, forgot something. Maximum number of turning points. What's the leading term? Cubed. What is your constant? What's your coefficient? Positive or negative? Power. Even or odd? What does F do on the left? Positive coefficient, odd power. What about on the right? What are the maximum number of turning points? What is the leading term? What is the coefficient? Positive or negative? What is the power? Even or odd? What does the function do on the left?
Increase.
What does it do on the right? Maximum number of turning points.
Negative over x.
What's your coefficient?
Negative
Is that positive or negative? What's your power?
positive.
Well, power has to be positive.
Even.
It's even. So you have a negative coefficient, even power. What does your function do on the left?
Go to negative. Or decrease.
And what does it do on the right? Also
Positive.
decreasing without bound. We can have no more than 3 turning points. All right, so should be pretty good at determining end behavior of polynomials now. We haven't discussed how to determine what it does in the middle. Other than we know the turning points, and we know what it's going to do at the intercept. But how do we determine the x-intercepts? And we know what the y-intercept is. And so that'd be a local behavior, whereas across the y-axis. We know how to find that. Just do f of 0. But how would you find the x-intercepts? The f of x equals 0. Solve for x. Go ahead, solve for x. And that's all. You don't have that technique from algebra. Because this is not quadratic form and is not an easily factorable polynomial. Right, you can't factor that by grouping. You really only have a trick for quadratics and linears and products of such. Well, that's the goal. When you're trying to find the zeros of polynomial, the goal is to write that as a product of linears and quadratics. Because then you can easily find the zeros. The problem boils down to how. So we want to learn how to factor a polynomial like that. That's what we spend the next couple of days doing. It is an easy process. It is very easy, but it's extremely long and tedious to do it by hand. Which is, of course, what we have to learn how to do first. Before before I then move on to count one and go, I'm just going to throw it into a calculator and find the zeros out. Then we have to determine multiplicities of the zeros, right? Because that's going to tell us what it does at the x-axis. Unfortunately, we are not going to be able to determine turning points that are not intercepts. That does require calculus to find those exact values. So again, let's just say that we know that those are intercepts. And let's just, for the sake of argument, say that they both have multiplicity of 1. So it's going to cross at both of them. And let's say we know that its end behavior is that. So the problem is, does it just go straight through like that on both sides? If we assume it does, fine. Which means we know it's going to turn down there. We know it's going to turn somewhere down there. But where? That we don't know. And that we can't figure out. Unless we know that the y-intercept is beneath the x-axis. Actually, even then, we don't really know. If I say that is the y-intercept, it doesn't mean that that's the turning point. So it could be that. We just don't know. That requires calculus. All we're going to be able to do here is get a rough idea of what it's doing. So any questions on end behavior, turning points? Interesting discussion. Starting with a review of the number systems that you learned in algebra. Actually, it's not just algebra. So starting with, starting your math career, the very first number system you learned to work with. I think it's 1. I don't think they do 0 first. I don't think they do. Because they tend to teach you how to count first, right?
Yeah.
And they start that at 1. It's called the natural numbers. Right? Some texts do include 0, others don't. I don't. Because the natural numbers are also known as the counting numbers. And you very rarely use 0 to count. Right? 0 represents the lack. did you work with after that? Which involved what kind of numbers? Integers. Right? The counting numbers, 0 and the negatives. What came after that?
Fractions.
Fractions. I think that's what, third grade?
Very good at that. Probably like 4%.
God, they're slow now. And so you learn the rationals next, the rational numbers. Which are any numbers that can be written in the form of an integer over a non-zero integer. What came after the rationals? That's still part of the rationals. You typically deal with the negatives as well when you learn fractions. After that, you then begin working with just all numbers in general, all real numbers. Which involves the rationals and what are known as the irrationals. The numbers that cannot be written in the form of an integer over an integer. Pi is irrational. Square root of 2 is irrational. What was after the reals?
Synonyms.
Which are called what? Complex. Right, numbers of the form a plus bi. A and b are real numbers. I squared is -1. That is actually where you stopped. That's as far as you've gotten so far. There are number systems beyond the complex. The next number system, called the quaternions. A plus bi plus cj plus dk. I, j, and k have special relationships. So the quaternions have 4 components. After the quaternions are the octonions, which are 8 components. Those are used when you start revolving space. So used a lot in advanced physics. After the octonions or the septernions, 16. And you can keep going up by powers of 2 from there. At the quaternions, you lose commutativity of multiplication. Now the order in which you multiply matters. At the octonions, you've now lost all of your known properties. You've now finally lost the associativity of multiplication. Grouping now matters. For the purposes of this conversation, we're going to stick with the complex numbers. How many natural numbers are there? An infinite number. However, it is countable. That way. We call it a left null. That is the smallest infinity. What about the integers? How many integers are there? More or less than the naturals? Neither. The exact same number. The integers are also countable. What about the rationals? Also countable. So they also have a left null. That's interesting. You would think that there'd be more integers, but there's not. You'd think there'd be even more rationals, but there's not. What about the reals? This is where you now lose countability. The reals are not countable. It's what's known as uncountably infinite. It's accepted that there are more real numbers than anything else. So the cardinality, which is just mean size, so the size of the reals are larger than the size of the others. But now what about the complex? They are also uncountably infinite. But are there more complex numbers than real numbers? There it is. It is accepted that the cardinality of the complex is larger than the cardinality of the reals. Which leads to an interesting consequence. Infinity is greater than infinity. But remember, infinity is just a concept, so that statement is actually kind of nonsense. But it does kind of give an idea that there's levels of infinity that we work with. The quaternions would be even larger. The octonions are even larger. So now you're building on infinity. And the question is, what is the largest infinity that we can reach? It is a very, very interesting topic. But this is why in calculus, you'll run into something like this. Infinity minus infinity. Which is not necessarily zero. Or something like this. Infinity over infinity, which is not necessarily one. or 1 to the infinity, which is really weird. Because you think 1 to any power is 1, but 1 to infinity is not necessarily 1. Can be anything. It's what's known as indeterminate. Or infinity to the infinity is indeterminate. My favorite indeterminate does not involve infinities at all. What's 0 to 0? Indeterminate. 0 to 0 is actually undefined. There is an interesting video. Vsauce did a very interesting video on infinities. I'm debating about whether I'm going to assign that later as a discussion. I already had the third discussion for week 6. Again, it's an interesting discussion about the use of AI in that. But I'm thinking about this. I actually assigned that video to my calc students when we were doing limits at infinity. So it's a very interesting discussion. And it kind of expands on the idea of infinity and what math is really about. So I might assign that video in a few more weeks. We'll see. Depends on my mood. So I want to note that I did skip a review of complex numbers. I did skip quadratic functions. If you want to read them on your own, go ahead. I think it's sections 3.1 and 3.2 respectively in the textbook. I'm skipping them because you should have done them in algebra. Honestly, the only difference with the quadratics is it's a more detailed explanation of quadratics. But it's nothing new. So I'm just going to do it. What we're going to do on Monday is look at dividing polynomials. So again, you kind of touched on that in algebra. Right, polynomial long division, does that sound familiar? Right, so you touched on algebra, we're going to expand on it. And we're actually going to use it for factoring, which is important for finding the zeros, which is what we do next Wednesday. And then, of course, you know the Monday after that, your first exam. So 2 more topics before the exam: dividing polynomials and finding the zeros. So there's the roadmap for the next week and a half. You have a homework due tonight. Have a wonderful weekend.